So now let us start with the derivation of the Z transform. So for that, let me consider some initial inputs, right? So first I consider my discrete time LTI system. So I consider this as my discrete time LTI system. I'll write it, guys. It is discrete time, what I can say, LTI system, right? Just a second. Yeah. So yes, it is a discrete time LTI system, and for this system what you're going to do is you're going to give your input x of n is equal to what? That is z to the power of n, right? This is what I call it as my what? Complex exponential input, right? So what is this? I apply a complex exponential input to, that is x of n is equal to z to the power of n to the discrete time LTI system, that is this one, and it is also consisting of along with impulse response h of n. So along with h of n you are going to apply, that is when you start writing the derivation you have to write, let us consider a complex exponential input, that is x of n is equal to z to the power of n to a discrete time LTI system with the h of n. H of n is what I say is called as my impulse response, right? Yes, it is impulse response. So you are going to apply to this. So now what is that output you are going to get? So output you are going to get is what I can say, the y of n. So what is your y of n? So your y of n is equal to what I can say, that is the h of n into x of n. Just a second. Yeah, it is your h of n into x of n. So this is what is your, what I can say, your y of n, right? So y of n. So now what is that you have to do is you are going to give this particular y of n to the this thing particular, right? This is what is the resultant y of n. So now what is your y of n? So now your y of n would be is equal to h of n into x of n, or I can write it as what? I'll rewrite that again and I'll show you. So this is y of n is equal to, that is h of n into x of n, right? So when you apply the x of n and h of n to the, what I can say, the discrete time LTI system, so what is that result you get it like? It is summation of, that is k is equal to minus infinity to what I can say, the infinity. So that is h of k into what I can say, that is x of, that is n minus k, right? So this is what is you are going to get. So what is this h of k first? So this h of k is what I can say is, when you apply h of n is applied to the discrete time LTI system, right? Discrete time LTI system. So you are going to get, so the discrete LTI, that is discrete time LTI system. So you can say that you get it as h of k, right? So now when you apply this x of n here, so this is the same. So x of n when you apply to the discrete time LTI system, so you're going to get this particular one, right? Yes. So now what you have to do now is, so the next procedure will come like this. What is the next procedure? So the next procedure will be, I'll just tell you, just a second, I'm erasing it. Yes. So my next procedure is what is, so now what you have to do here, you know that your, what I can say, I'm really sorry, did not take this. Yes. So yes, next procedure is what? My next procedure is, so this is x of n minus k now. Okay. So now you know that, so here x of n is equal to z to the power of n, right? We have already told in the beginning that we are giving here x of n is equal to z to the power of n to what? To the discrete time LTI system, right? So this is x of n is equal to z of n. So now as this is x of n minus k, now what is that going to happen is here z to the power of n will become equal to z to the power of that is n minus k, right? Yes, what I can say here, z to the power of this thing, I'm sorry, x of n minus k will become is equal to that is z to the power of n minus k. So now that one we are going to substitute it over here. So here we are taking x of n minus k as z to the power of n minus k. Right? You got it? Yes. So I'll re-repeat this whole slide once again. So this is your y of n, that is equal to h of n into x of n. So what did we learn till now? We learned that we have given x of n is equal to z to the power of n to what? That is discrete time LTI, that is what I can say, linear time invariant system, and along with this h of n, that is what is h of n? Your h of n is what I can say, the impulse response. So when you give that to that particular this system, that is discrete time linear time invariant system, so your output y of n, that is the system output is what? That is h of n into x of n. So h of n into x of n, and what is that going to happen is you are going to get the resultant like this. So this resultant is, so that is summation of k is equal to minus infinity to infinity h of k into x of n minus k. So what is h of k? H of k is when you get the z transform, or when you apply the z transform of that is h of n is h of k, and x of n z transform is x of n minus k, right? And so therefore now we know that your x of n is equal to z to the power of n. So for x of n minus k, it becomes equal to z to the power of n minus k. So that is what we learned till now. And now next what are we going to do is we are going to write in terms of that. So that is what you are going to write it like, that is your what I can say, the x of n into, so summation of that is what I can say in k is equal to, so what I can say, the minus infinity. Just a second guys. Yes. Yes, here k is equal to minus infinity to infinity. So that is here what I can say, the h of k into that is z of n minus k, right? Did we substitute? Yes, so we substituted. So now what is that going to happen is, so now here we are going to take z of n to outside, right? The z of n will come here. So now what is that going to happen is, I'll erase this and I'll write it smaller. Yes, so I guess you got it till now. What is that, right? Yes. So now see here, this z of n will come to here. So when it comes to here outside, what is that going to happen is you get z of n into that is summation of that is k is equal to minus infinity to infinity. So you're going to get that is h of k into, so that is what your z of minus k. So now here you can see that, so I'll take this color now. So see here you can see that, so this particular part excludes z of n now. So take this particular part. So what is this particular part? So this particular part, what I can tell it as h of z, right? So what is my h of z? That is summation of k is equal to minus infinity to infinity. So that is h of k into z to the power of minus k. So now after this, so we'll write this equation in a very simplified form. That is what I can say here. So z to the power of n into h of z, or I can also write it as that is h of z into z to the power of n, right? I guess you got it right. So this is what, so I'll retell it this slide again. So this is what, so this is what is your x of n minus k is equal to z to the power of n minus k, that what I told you, that is part of this. And now what did we do? From here we just omitted z to the power of n to outside, that is outside. So that is why here z to the power of n came here, and we now got an equation like this, that is summation of k is equal to minus infinity to infinity, that is h of k into z to the power of minus k. So this is what is we can call it as h of z. So therefore I got this particular. I guess you got it right. Yes. So now next what you have to do is, you can even write your h of z in another manner. So how can you write your h of z? So your h of z, we already know that it is summation of k is equal to minus infinity to infinity, that is your h of k into z to the power of minus k. I told you already. But you can also write it like this, that is summation of n is, you can write it in terms of n. So n is equal to minus infinity to infinity, that is your h of n into z to the power of minus n. So this is what you can write it in terms of n, right? Yes. So now you can also tell your h of z as what, that is the z transformation of h of n, right? h of z is z transformation of h of n, right? Yes, that is z transformation of what I can say, the h of n, right? Yes, that is what you are going to write. So now coming on to so now next thing what you have to do is you are going to consider the z transform of x of n. Now comes the z transform of x of n. So what is your z transform of x of n? So your z transform of x of n will be is equal to that is what I can say here, x of z, right? Yes, just a second. Yes. So your z transform of x of n is equal to what? That is your x of z, right? So now what is x of z? So now your x of z is equal to, that is your summation of infinity to, that is n is equal to minus infinity. So therefore that is your x of n into z to the power of minus n. So here we are writing it in terms of n, right? I guess you got it. What is this? So now the next procedure comes into picture, that is what, you are taking your z. So you are taking your z and you are defining your z as a complex variable. So what is your z here? Your z here is a complex variable, and yes, z here is a complex variable, and which is equal to r e to the power of j, that is omega, right? So now I'll rewrite that once again, and here your z you are considering it as a complex variable, so that is which is being given by, so that is your z is equal to r e to the power of j omega, right? I'll write that now. So which is equal to what? It is equal to r e to the power of into e to the power of, I'm sorry, it is j omega, right? So now e to the power of j omega, you know, that is cos omega plus j sin omega, right? E to the power of j omega is what? Cos omega plus j sin omega. So that is what you are applying it. So let me write that also. E to the power of j omega is equal to cos omega plus j sin omega. So that is what you are applying over here. And what is the resultant you are going to get here is, that is you are going to add r here. So that is r cos omega plus what I can say, that is j, what I can say, the r sin omega. This is what is you wanted, right? Yes. So this is what is that particular r e to the power of j omega, right? So now that is, you can also write it as, that is r e to the power of z and plus j into imaginary of, that is z, right? Imaginary of, that is z. And so therefore now coming on to this, so here this is just for your understanding we have written this, so this is not of much importance, this particular one, so you can just leave it off. And here next you can say that what is r and omega, and r and omega, right? Here this r and this omega, you need to know what. So what is this r? This r is what I can say the magnitude, and this is omega is the angle with respect to z, right? Angle with respect to z, right? Yes. So now you understand till now. So here what did we do? We considered this z as a complex variable. So where was z? So that was where it is what, where it is x of n into z to the power of minus n. So there was a z, and that z we are considering as a complex variable, and we are also telling that z is also defined by r into e to the power of j omega, wherein that you can write it as e to the power of j omega. I can tell it as, that is cos omega plus j sin omega, that is this particular. So we use the same here, and we wrote it as r cos omega plus j into r sin omega. And so therefore we define what is r. Here r is the magnitude and omega is the angle with respect to z. So this is what is that. And next one, coming on to this next one. So what is next one? Your next one is, so we know that what, your z is equal to r into e to the power of j omega, right? You know that it's r into e to the power of j omega, and let us substitute this where, in that particular equation. So which equation if I write, you will get to know. So that is n is equal to minus infinity to infinity. This is x of z equation. You are going to substitute. So that is, you are going to get x of n into, that is you have, that is z to the power of minus n. Now what we are doing, in the place of z we are going to substitute r into e to the power of j omega. So that is why what I will do is I will directly write that. So let me write that as r into e to the power of j omega, that is whole to the power of minus n. So now what is that going to happen is, we are going to take e to the power of minus j omega n to outside. So what does that become now? That becomes your summation of infinity to n is equal to minus infinity. So that is what is your x of n into, so just write a flower bracket over here. So that is x of n into, I told you that you are going to keep x of n into r to the power of minus n, and you are going to omit, that is e to the power of minus j omega n outside. So we did what? So we took r to the power of minus n inside. So we took this 2 as inside, and we omitted that e to the power of minus j omega n outside, and we wrote it, right? So this is what we did right now. So now you can see that, so this particular part is what? So this particular part is what I can say, that your x to the power of, what I can say, the r e to the power of jn is equal to, or you can say x of z. So see here, for this z also you can directly substitute this r e to the power of j omega, right? J omega. So that is equal to what? The Fourier transform of, that is x of n into r to the power of minus n. So let me write that. So yes, so see here, it is here what I can say, the this one, that is the x to the power, x of r e to the power of j omega, which is equal to what? That is Fourier transform of, that is x of n into r to the power of minus n, right? Yes. So that is what is he has told, right? So from this particular one only you can see, so this x of, that is r e to the power of j omega, will is equal to this Fourier transform of this particular x of n into r to the power of minus n, right? So now this is what is the given. So now next what you are going to see, that you can see that there is r to the power of minus n. So now we have described this r to the power of, what I can say, minus n. So what is r to the power of minus n? So maybe decaying r to the power of minus n, it may be a decaying or growing signal with respect to what? Yes, decaying or growing with respect to, that is your n, right? Decaying or growing with respect to increasing of n, and whether or depending on whether r is greater or lesser than unity, right? So it is an decaying or growing with increasing n, right? So this is a just a second, I'll write it with increasing n. So this is, I also can call it as what? My exponential weighting factor, right? This is, I can call it as my exponential weighting factor. So that is what I can say, the r to the power of n. I'll also write that, I forgot that, I'm really sorry. It is exponential weighting factor, right? Yes, exponential weighting factor. So it is exponential weighting factor. So it is decaying or growing with increasing n, and along with it is depending upon whether r is greater than or lesser than unity. So therefore what my equation would become equal to? So my equation would become equal to, so that is x of n into e to the power of minus j omega n. So here we are omitting, so that is, here we are omitting r to the power of n. Why r to the power of minus n there? Why? It is because if for a z trans, that is a signal to converge, so your r should be 1, or that you can say that your z modulus should be is equal to 1. So therefore we are going to omit r to the power of minus n. So now if you omit r to the power of minus n, so you get the equation as, that is summation of infinity to n is equal to minus infinity. That is what I can say, your x of n into, that is e to the power of minus j, that is omega n. So here we omitted r to the power of minus n. It was there, you saw, right? So we omitted that because as r is equal to 1, so here z bar or is to z modulus also is equal to 1. I'm sorry, this is z modulus. So z modulus also is equal to 1. What that means is that for a signal to converge, so your condition should be your r is equal to 1 or z modulus is equal to 1. So therefore that is, you can say that if your r is becoming 1, so what is 1 to the power of minus n, which is also is equal to 1. So therefore we are omitting that, and we got this particular, right? So now you can say that, so that is x of, that is e to the power of j omega, which I can say that it is equal to what? That is x of z, for z is equal to e, that is e to the power of j omega. So here x of e to the power of j omega is equal to x of z for what? That is z is equal to e to the power of j omega. So this is what you got it, right? So it is nothing. So what did we do? We considered here r is equal to 1 and z modulus is equal to, that is 1, and we omitted r to the power of minus n here as r is equal to 1, and then what we got is, we got this, that is x of n into e to the power of minus j, that is omega n. And what is that happened is, we got to know that your x of e to the power of j omega is equal to x of z, for where z is equal to e to the power of j omega. If your z is e to the power of j omega only, your x of e to the power of j omega becomes equal to x of z, right? Yes. So now coming on to my next one. What is my next one in the derivation is, you can see the z plane. So the z plane is really important for you because you need to construct it for each and every question, right? And now what is your z? Your z is equal to r into e to the power of, that is what I can say, the j omega, right? So this is my what I can say, the signal. So this signal, what you can say, so here your signal is a that z point, the point said, that is your r, z is equal to r into e to the power of j omega is located at a point r, that too at an angle, what I can say, that is omega, right? It is located at a distance r. So this distance is r. I'm sorry for it, just I'll rewrite it. Yes. So this is a z is equal to, it is at a distance r, and then it is having an angle of that is omega, right? This is what is the r e to the power of j omega, right? I guess you got it right. Yes. So this is what is that. And so therefore here you can see that the range of r for which the condition is satisfied, so you, that is what is I call it as region of convergence. So what is region of convergence? That is ROC. Your ROC is what I can say that the range of R. So the range of R for which the condition is satisfied. So you can see that. So for which the condition is satisfied. So you can say that it is my, what I can say, the region of convergence. So right, that is what is for this derivation. Okay. So in this derivation, what did we do? We just first took what? We first took the x of n is equal to, that is z to the power of n, and along with the impulse response, that is h of n, what did we do? We multiplied what? We got the system output. So that is, we gave that particular x of n and h of n to the discrete time LTI system, and what did we do? We got the system output, that is y of n is equal to, that is h of n into x of n. So that is, we also can represent that as, that is summation of, that is your k is equal to minus infinity to infinity, what I can say, that is your h of z into x of n, x of, that is what I can, h of k, I'm sorry, h of k into, that is x of n minus k. So what is x of n? So x of n, we knew that it was z of z to the power of n. So therefore your x of n minus k would become equal to z to the power of n minus k. So what did we do? We substituted in the place of x of n minus k, that is z to the power of n minus k. There we omitted z to the power of n outside, and we got one equation as, that is what your summation of k is equal to minus infinity to infinity, that is h of k into, what I can say, that is the z to the power of minus k, and that is what we call that as your h of z, right? We call that as h of z. And then what did we do? We just took the h of z in terms of n, that is, you got it as x of n into, that is h of n into z to the power of minus n, you got it. And then we took the, that is z transform of x of n, that is your x of z, and we solved with respect to x of z, and we took a z as, that is r e to the power of j omega, and we just substituted that also in the particular x of z, and we just got the resultant. And now at the last we wrote about, we talked about, that is the r, that is what is r to the power of minus n, and then we wrote this particular diagram over here, wherein this diagram is really required for your, what I can say, each and every problem, right? So we are not going to write like this, we are going to write a circle there, right? We are going to write a circle there. So that is what we are going to do. And we also learned about what is ROC. So what is ROC? Your ROC is also can be told that for a range of R in which the condition is satisfied. So that is what is, I call it as my, what I can say, that is the ROC. So that is the region of convergence. So this is what is for derivation session. So let us meet in the next session, that is your region of convergence properties, right? Yes.